Inverse functions. An inverse relationship interchanges the input and output values of the original relationship. The table of values that I have here are ordered pairs that work for the equation y equals negative 2x plus 6. For example, if you were to plug in 0, this would cancel out and you get 6. Okay, so that's a table of values that works for this equation. And what I'm going to start with is going ahead and making a graph of that. And I can either just plot the points or use the equation to do this. I'm going to go ahead and just use the equation. This has an intercept at 6, which would be here. The slope is going to be down 2 over 1. So you get a point here, 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 and here. Okay, and what I'm going to do is highlight these points because that might be useful in a bit. The inverse relationship is going to switch the inputs and the outputs. So what I can do is take this table of values and just switch those numbers. So I get 6, 0, 4, 1. This is going to be 2, 2. That one doesn't change. We get 0, 3, and negative 2, 4. And I'm going to go ahead and graph those. At 6, 0, we get a point here. We've got 4, 1, which is here. 2, 2 is the same point. We've got 0, 3, which is here, and we've got negative 2, 4. Okay, so as a graph, that represents the inverse relationship of the original relationship. As we take a look at both of these graphs, you're going to realize that what we actually have here are functions because they both pass the vertical line test. That would allow us to rewrite the equation as f of x. We can say that f of x is equal to negative 2x plus 6. Then the inverse function, okay, so not just the inverse relationship, but the inverse function can be written this way. You can use f with a negative 1 as an exponent of x. And you read that as f inverse of x or the inverse of f of x. This does not actually represent an exponent. It would just be a notation that indicates that this is the inverse of that. And we can write an equation for that one. It does have a slope of negative 1/2, goes down 1 over 2. It also has an intercept at 3. So this would be the inverse of f of x is equal to negative 1/2 x plus 3. The graphs do share one point, which is going to be at 2, 2, because at that point, y does equal x. Okay, you're going to notice they cross each other right there. They match up to each other. One additional thing we can do to highlight this, we can actually draw the line y equals x, which is going to be that perfect diagonal with a slope of 1. And you'll notice that f of x and the inverse of f of x are actually reflections across that line. For example, they meet at the same point, they cross there. But you can look at certain coordinates, such as this and this, and realize that if you were to fold this in half, these two would match up, these two would match up, these would match up. Those are easier to look at because they're actually intercepts. Okay, the x-intercept of 6 matches the y-intercept of 6, and so on. All right, so there's a lot of things we've already looked at with respect to inverse relationships or inverse functions. To be an inverse, the inputs and the outputs will flip-flop. Graphically, they're going to be reflections across the line y equals x. And in addition, if we use this notation, f of x and f inverse of x, we can use that to describe that they are inverses. So you can use other ones as well, like g of x and the inverse of g of x, or h of x and the inverse of h of x. Example 1. Find the inverse function by interchanging the variables. Okay, so what this is an algebraic technique that you can use to take an original function, such as this, take an original function, the same one we had at the very beginning, and algebraically write what would be the inverse function to that. Okay, so from the very beginning, my statement was that an inverse relationship or an inverse function interchanges the inputs and the outputs, which would be the x's and the y's. So what we're going to do first is take our function and replace f of x with y. Mostly that's going to be done just so it's easier to look at the variables. Okay, and then what we're going to do is switch the x's and the y's. So we get x is equal to negative 2y plus 6. And in a sense, we have actually created the inverse already. It doesn't look good. It's not in function notation. You don't have the y value, which is the dependent variable isolated. But as you choose certain values to plug in for x's and y's, the ones that will work together will actually graph the picture of the inverse. All right, so all we're going to do next is solve for y, so that we can then get it into function notation. All right, to solve for y, we're going to start by subtracting 6. Okay, so we got x minus 6 is equal to negative 2y. We will then divide by negative 2. At this point, the y value is by itself. And in a way, you can just let that be your answer. But to make it match what we did earlier, I'm going to go ahead and divide both of these terms by negative 2. Okay, so it's going to look like this. Okay, the coefficient of x is 1. So if you divide by negative 2, you get a coefficient of negative 1/2. Negative 6 divided by negative 2 is positive 3. And we should see that that is the same equation we had earlier based off of the graph. All right, to restate in function notation, we're going to take the y out. For example 2, we're going to find the inverse of g of x, which is 4 minus x squared. It does have a limited domain of x greater than or equal to 0. We're going to verify everything with graphing as well. In fact, what I'm going to do is start with the graph of g of x with that restricted domain. Okay, so the graph of this function would be a parabola because you have the x squared. With that negative coefficient in front of it, it's going to flip it upside down and open downward. The 4 is going to shift everything up. Instead of having the function here, it's going to get pushed up by 4. It's also going to get flipped over. So we're going to have a point here. We would have a point here and here as it opens up. But because we've got a restricted domain where x is only going to be positive or 0, that isn't going to be part of it. All right, the next point beyond there is going to be here. All right, so that's g of x. The inverse of this will end up being the reflection across y equals x. So let's add that in. Okay, so g inverse of x should be a reflection across that one, which means that this point will end up here. They're going to share that point. This point is going to be here, and that intercept is going to be here. Okay, so here's our graph. Of the inverse of g of x. All right, and now what we're going to do is algebraically solve for that. We're going to take the original function, go ahead and rewrite it with a y. We're going to switch the x and the y. Then we're going to solve for y. So we're going to subtract the 4 to the x. We can undo that negative by flipping that around. So you get 4 minus x is equal to y squared. You can then take the square root of that. And this will represent our inverse function. So the inverse of g of x is going to be equal to the square root of 4 minus x. And last, let's just verify that this does go with this graph. And there you go. You've got that intercept at 4. It's also going to be crossing at 2. You got that intercept at 4 and crossing at 2. An inverse function can also be thought of as a function who undoes what another function does. Formally, two functions f and g are inverse functions if g of f of x equals x or f of g of x equals x. In other words, whatever f of x does, when you put that function into g of x, everything will be undone and you get back your input. Or whatever g of x does, when you put that into the f of x function, everything will be undone and you get back your input x. So it doesn't matter which way you build the composite, but those composites would cancel out everything that the other one did. Example 3, use composites to show f of x, which is equal to negative 2x plus 6, the same function that we had at the very beginning, and g of x, negative 1/2 x plus 3, are inverse functions. All right, so let's build some composites. We'll do this first. G of f of x. Okay, what I'll need to do for that is build a shell using this. And in the parentheses, I'm going to drop in f of x. And now all I'm going to do is reduce, perform some operations. What I would start with is distributing the negative 1/2 into the parentheses. Okay, negative 1/2 times negative 2 is going to become a positive. Half of 2 is going to give you 1, so basically just becomes an x. The negative 1/2 times positive 6 will give you negative 3. We still have the plus 3. These will cancel, and you get x. All right, so the other way we could do this, we could do f composite g of x. So we'll build a shell with this. In the parentheses, we'll drop in g of x. We'll distribute. The same thing happens right here. That just becomes a 1. So you get x. You do get a negative 6. You also have the positive 6, which will cancel, and you get back to x.
Wait, what?